Hello students! In this video, my purpose is to explain how we develop the formulas that we're going to learn in our lesson today. So watching this video is optional. If you feel like you just can't handle another day of long videos, and if you're okay with not seeing how the formulas are developed, then just don't watch this video and skip on to the next one where I present to you the formulas and we do an example. And that video should be pretty short. You don't need to take notes on this video, so if you're interested in seeing how we develop the formulas and you have time, then continue watching. So we're going to talk about compound interest today. And compound interest is where you have an investment, you earn interest, and then you leave your money in the investment so that you can earn more interest, and what ends up happening is you earn interest on your interest, and that means it compounds and you get more and more money. So let's work our way through this scenario, and it's going to help us to develop a formula. If you invest $500 at 6% annual percentage rate, what will the balance be at the end of 1 year? Okay, so what we need to do is we need to take $500 and multiply it by 1.06, because that would be 100% of your money plus the extra 6%, the percentage rate. So if we just multiplied it by 1, that would mean we would have our original $500 back, but by multiplying it by 1.06, we end up with $530. So that's the final balance. If the question was, what's the interest, you would just say the interest is $30. But if the question is, what's the balance, it's the principal plus the interest. Okay, part B. Now we're going to invest that money for 2 years, not 1 year. But we make 6% per year. So what happens is we take our $500, we multiply it by 1.06 for the first year, and we know that gives us $530, and then we multiply that by 1.06 for the second year. And of course, we could write that as 500 times 1.06 squared, and that gives us $561.80. So you can see in year 1, $30 interest was made, but in year 2, $31.80 interest was made, and that's because we got interest on our $30 from year 1. So continuing on to year 3, we have 500 times 1.06 to the third power, and we get, and I'm going to have to round this to the nearest penny. I don't have to, I guess, but I'm going to round it to the nearest penny. $595.51. And I'm just going to make that an approximation sign. So we see that each year we're earning just a little bit more interest than we earned the last year because we're earning interest on our interest. Now let's generalize this, and we can say that we have 500 times 1.06 to the t power for t years. So you can imagine how we could generalize this more. So instead of using 500 for the amount invested, by the way, the amount invested is called the principal. Instead of using 500, we could use a variable there, typically a p. Instead of using 0.06 for the interest rate, we could use a variable there, typically r for rate. So we're building a formula, but there's one more thing to consider. So, interest is not always compounded annually, meaning just at the end of a year. Sometimes interest is compounded semi-annually, quarterly, monthly, daily, etc. So multiple times per year. So let's work through these scenarios. If you invest $500 at 6% APR for 1 year, how much money will you have if the interest is compounded in these various ways? So notice that we're keeping the amount of time the same in this problem, just 1 year. Whereas in problem number 1, we changed the time. Now we're changing the number of compoundings per year. So in part A, it's just like we did with number 1. It's $500 times 1.06. So we get $530. Now for part B, semi-annually means 2 times per year, once every 6 months. So what happens is you don't get 6% at the 6-month point and another 6% at the 12-month point. You get 3% and 3% to add up to 6. So that's going to look like this. 500 times 1 plus 0.06 divided by 2. See, there's your 3%. It's happening twice in a year, so we're going to multiply by that twice, so I'm going to raise that to the second power. Another way to write that out would be take your 500, multiply it by 1.03 at the end of 6 months, and multiply it by 1.03 at the end of 12 months. So that's the same thing as what I wrote above. And we can calculate that. I might have to round, we'll see. Looks like no rounding needed, $530.45. If interest is compounded quarterly, that would be 4 times per year. Once every quarter would be once every 3 months. So we have $500. Multiply that by 1 plus 0.06 divided by 4. So that would be 1.5% every 3 months. And that's happening 4 times. So hopefully you can see by the way I'm writing this, here and here, that this is going to help us develop a formula. And so we can put this in the calculator, and rounding to the nearest penny, we get $530.68. So notice that every time we increase the number of compoundings, we increase the interest a little bit, from $30 to $30.45 to $30.68. Now let's move on and do monthly. So that would be 500 times 1 plus 0.06 divided by 12 to the 12th power. And for that we get approximately $530.84. And then daily. So for daily we just use 365. We don't worry about the whole leap year thing. So we have 500 times 1 plus 0.06 divided by 365 raised to the 365th power. And rounding to the nearest penny, this one gives us $530.92. So you can see that even though the interest is continuing to increase, the amount of increase is not that big. We're kind of reaching an asymptote, actually, where the amount of increase gets smaller as you go, and so eventually the amount of increase is so tiny that it's negligible. Now for a generalization, for n times per year, we would have our $500 times 1 plus 0.06 over n raised to the nth power. And again, we're going to generalize this where we don't use 500, we don't use 0.06, and also, what if instead of it just being for 1 year, as we've done on this entire page, but what if it was for t years, then we would also have an extra variable up there. So that's what we do to get to our formula, which is right here. This is called the non-continuous compound interest formula. The next formula we learn is going to be continuous compound interest. So we have A, the final amount of money after t years, equals P, the initial dollar amount, known as the principal, times the quantity 1 plus r over n to the nt power, where r is the interest rate converted to a decimal, n is the number of compoundings per year, and t is the time in years. So the reason we have to multiply n times t in our exponent is because, let's say you were compounding 12 times a year for 3 years, that means there would be 36 compoundings. So 12 times 3 is 36. So I'm going to present this formula again in your notes video, so if you're just watching this for the information, you don't have to be writing this down right now. Okay, we're going to move on to another derivation, and I'm going to use a graphing calculator to help me with this. So imagine that I take $1 and I invest it at a 100% interest rate for a year. Let's find the amount of money in the account if it's compounded n times per year for these different values of n. So using our formula that we just saw on the previous screen, we're looking for A, the amount. We're investing $1, that's the principal. The interest rate is 100%, and when converted to a decimal, that's a 1. We're going to try different values of n, and we're doing this for 1 year, so it's just to the power n times 1. And we don't need this initial 1 here. So what we're doing is 1 plus 1 over n to the n power. And in the calculator, it's going to be 1 plus 1 over x to the x power. So I'm going to put that in my graphing calculator as y equals that as a function. Even though I'm not interested in graphing it, I'm interested in using the table. And in order to use the table, I need to put that into the y equals menu. So then we're going to type it in. So y equals 1 plus 1 over x to the power of x. And then I'm going to go into table set, which is second window. I'm going to make sure it's on independent ask, which allows me to type in my own numbers. And then second graph takes us to table. And I don't remember exactly the numbers, but the point is they're going to get really big. 10 compoundings per year, approximately $2.59. 100 compoundings per year, approximately $2.70. 1,000 compoundings per year, approximately $2.72. 10,000 compoundings per year, approximately $2.72. Now, if you move your cursor over to the y column, you can see more detail for that y value down at the bottom, more than they could fit in the column. So you can see that even when I do the next one, 100,000, in the table, or even, let's do 1 million. In the table, those two y values might look alike, but actually, they're slightly different. They have very, very small change. So what's happening? As the value of x gets larger and larger, how about 1 times 10 to the 10th power? We are getting a number, we're kind of encroaching on this number, 2.71828 blah, 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 blah. It's actually a very famous irrational number, just like you know pi is a very famous irrational number, and pi is used primarily with circles. Well, this number, which we call e for a mathematician named Euler, is used primarily when it comes to the growth of things or decay. It could be the growth of money, as we see here. It could be the growth of bacteria, the growth of a population, the decay of a radioactive substance, all kinds of things like that. And we will be doing more examples of that as we get to the end of our chapter. So what we have now is the number e, lowercase e. It's known as the natural base. It's irrational. Its approximate value is 2.71828. Just like when you want to know the approximate value of pi, you probably say 3.14, or maybe you say 3.14159. For the value of e, the approximate value, I would say 2.718. And if you want to go further, obviously you can. Here's the exact definition of e, one of the exact definitions of e. There's a few, depending on what branch of math you're looking at. And what we see here is that we have this expression that we had typed in the calculator with an x instead of an n, but it's the same thing. And what we're doing is we're finding what happens as n goes toward infinity. So we call that a limit. As n gets bigger and bigger and bigger, what are we getting? We're getting this number e. Now, since e is a number that is greater than 1, if you were to graph y equals e to the x, you would get an exponential growth function, just like y equals 2 to the x or y equals 3 to the x. Oh, those are just empty boxes. Okay. Now, to finish this informational video about how we derive the formulas for today, I'm going to do a kind of a compression, or let's call it a marriage, of this formula and this formula. So you have arrived at the wedding for the compound interest formula and the definition of E. Let's say I want to know what happens if I compound interest infinitely many times per year. That's not physically possible, but this is more of a theoretical thing. Like a mathematician might think, what happens if I just take this to the extreme? So what we can do is kind of combine these. So what I'm interested in knowing is what happens as n goes to, oops, that's not an n, as n goes to infinity. Now, there's some things you haven't learned about limits that you'll learn in calculus that you're just going to have to take my word for it right now as I do this proof. One is that if you have a constant like p, you can factor it out of the limit. So I'm going to do that. Now you might notice that what I have here as a limit looks kind of like the definition of E, but not entirely. So what I'm going to do is some mathematical gymnastics and some substitutions to try to get my limit to look more like the definition of E so that I can substitute E in there. So what I'm going to do, first of all, is I want to remember that the letter N is not important in this definition. This could be an X, this could be a K, this could be whatever letter you want as long as it's consistent throughout the whole definition. So I'm changing it because there was an N over here, and this N over here is not necessarily the same N, and I don't want to get confused by that. Alright, so suppose I say let X equal N over R. So that means that 1 over X is R over N, the reciprocal. So what I'm going to do is replace R over N with 1 over X. So now I have P times the limit as N goes to infinity of 1 plus 1 over X to the nt. So we've made a little progress because we have this part of the definition of E. There's still a little bit to do. So now I need to get rid of the n that's in my exponent. So according to this statement, n would be equal to r times x. So let me go ahead and replace n with r times x. Oops. Okay, then the next thing is that if n is heading toward infinity, and r is just a finite number, that's our interest rate, then r times x is also heading toward infinity, and so x is heading toward infinity. So I can change my limit to say x goes to infinity instead of n. Also, remember that multiplication is commutative, so we can rearrange the order of those letters. So that could be written as XRT. Now if you look at the definition of E, and you look at what I have here, we're just inches away. So what I'm going to do now is use exponent properties and think of this as to the x power and to the RT power. So power to a power, you multiply the powers. So now we can replace this entire thing with E. So we have P times E to the RT. And that's the final amount of money if you invest continuously, if your compoundings are continuous. So that gives us this formula for, oops, it should say continuous right here. Continuous compounding. A equals PE to the RT. Sometimes people call it PERT. It's the PERT formula. Okay, so that takes us to the end of this video where we've just been deriving the formulas, and so in your lesson video when you take notes, you're going to get to use these formulas. Thanks everybody.